My name is Albert Wildeman, by the way. If you have any questions, just say Albert. So if you remember, Wim spoke last time about Fourier series. So he started with the real and then went to the complex. And really what these are ways to approximate any function in the time domain as a sum of sinusoids. So it's a way of decomposing any arbitrary function into a sum of sinusoids, looking at getting information as to how much of every frequency makes up your function. And one of the ideas there was that as you take the sum further and further, you get a better approximation of your function. And what we're going to do today is talk about the Fourier transform, and it really extends that idea by instead of taking a discrete sum and summing more and more elements, we're actually going to push that to the limit and end up with a continuous function. So instead of all these discrete elements, sinusoidal elements, we'll have a continuous sum of sinusoids, if you will. All right. To start, I'll just reiterate the complex Fourier series. So we will be deriving this from the complex version, which is, if you remember, like completely equivalent to the real one. So we have a sum with, in principle, infinite elements. Cn, the coefficients. And the exponential term, so Jn, omega naught, and t. And go to this side for the coefficients. Here we have the period. And we have the period because for the Fourier series, you're looking, by definition, at periodic signals. So this is the period of the signal that you're looking at. And integrating over one full period, any period, your function ft exponential term, and closing the integral. So the Cn's are our discrete collection of coefficients, and we're going to make those into one continuous function. We're going to have to make some changes. So I'll call this Cn star. I'll start with that limit. And we'll really be doing two things at the same time. Because if you'll remember that, put this here. So the base frequency is inversely proportional to the period of your signal. And this equivalence, or inverse equivalence, means that taking one limit is really equivalent to taking the limit in the other. Sorry. This one goes to 0. And this is related to the motivation of what we're doing here. So W naught is going to 0, which means that this here, the NW naught, is the steps between the frequencies of the sinusoids in our sum. And we want those steps to become infinitely small. So the way we do that is by letting W naught go to 0. Now as we do that, by this relation here, we also have that the period goes to infinity. What that also does is, if you think about what periodicity means, so the period is the amount of time after which the signal repeats. So for the period to go to infinity means that you're no longer really repeating your signal, right? You only repeat it when you get to infinity, which you never get to. And this means that we're also generalizing now. So we're going to be able to apply this to any function, not just a periodic function. All right. Still going to be taking the integral. And here the T naught meant just take the integral over any period. And right here I'm centering that period around 0. Ft remains the same. And the exponential term also remains the same. All right. Now as we're going to actually take this limit, we're also going to use some different notation. So capital F of j omega equals the limit from minus infinity to infinity, because t naught goes to infinity, over still the same f of t but now the exponential becomes j omega t. And this is because the n omega naught were the steps. So n times omega naught were the different points on the frequency axis. Right now we don't have points anymore, or like discrete points, but instead we have a continuous variable. And it became an argument of the function, rather than an index to the coefficients. All right. Now this is already our Fourier transform. The one thing I did do is here, forget about the T naught. So this vector, I dropped in this step, but I'll take it back in when I go back from the transform, so from the frequency domain back to the time domain. And for that we'll look back at this. Because Pt is really our Ft, right? Expressed as a sum of sinusoids. And now let's look at Cn again. So we're going to be working back to the time domain in steps. This is where I'm going to be taking back that factor of 1 over T naught. So it comes from all the way over there. And here our Fourier transform. However, note the argument here. So because we're looking at Cn, which are the coefficients, and there's a discrete number of them, because we want to use this continuous function, we're only going to take a discrete number of values out of it. So that's what we're doing here. So we're not using the whole function, but picking values from it. And this we can plug into our expression for Pt. Now let's include this. So this is basically a way of expressing that Pt is indeed f of t, but only on this period T naught. This is where we'll fill in the expression for Cn into the formula above. We'll have our sum. Uh, 1 over T naught, our f, and the exponential. All right. Now what we're going to do is, because we still have our T naught in there, we're going to be taking the same limit as we did before. So to get to f of t, So this is exactly the same limit as on the left side there. We're going to... So where that comes from is, here it is 1 over T naught. So 1 over T naught is W naught over 2 pi, by this formula here. And we'll deal with the W naught later, but I'll take the 2 pi here. Then still the same sum, minus infinity to infinity. And the same f and the exponential. And here, the omega naught. Now, as to taking that limit. So the 2 pi will remain, 1 over 2 pi. The integral the sum turns into an integral, because once again these steps n omega naught are becoming infinitesimally small, so we're going to an integral. Minus infinity to infinity. We're back to the notation of j omega, because we're no longer taking discrete steps. The exponential, j omega t now, and d omega. So the one thing that might strike you as a little odd here is the omega naught disappeared. And the way to think about that is that the integral, as it relates to the sum, is really the area under the function, right? So this sum is also calculating the area under a function. And for each element, or for each little bit, the area means multiplying the value of the function. So that's the f times the exponential. But you have to multiply that with the width of the little part you're taking. And that's the omega naught. It's the step in the frequencies. And really, where that goes is it goes into the d omega. So it becomes the infinitesimally small part over which you sum the areas. Is this clear so far? Is this making sense? Any questions? All right. I'm going to wipe out some of this. So these two expressions that we found, the Fourier transform and the inverse, these are for continuous functions, right? So these are continuous functions of time transformed into continuous functions of frequency. And that works very nicely for analytical things, but typically when you do experiments and have data, you have sampled data. And for that, you would really want something equivalent to this, but for discrete time. And for that, you can use, unsurprisingly, a discrete Fourier transform. So we'll derive that next. So let's do the transform first. So from the time domain to the frequency domain. Instead of f of j omega, let's call this fa. Of j omega k. Because time is discretized, frequency will also be discretized. And we're just going to derive it from here. So instead of the integral, we're going to have a sum. Over a discrete amount of, finite amount of elements. We're going to have our f taken at Tn, so no longer at continuous t, but at points Tn. And the exponential now has both discrete frequency and discrete time, so omega k and Tn. And the time step. So at this point, let's note the formulas for the time steps and the frequency steps. The time step we're taking as n delta t. So this is simply evenly sampled data in starting at 0 and incrementing. You might not always have that, but as long as it's evenly sampled, you can map it onto this. And if it's not evenly sampled, there is a good way to deal with it, and it's Lam's algorithm. It's described in the first chapter of the second book, of the 2010 book. And we might have time to talk about it later in the course, but if you are interested right now, you can look at that or ask any question to Wim or me. All right, so we have the time step, the frequency step, or rather, the frequency points are the index for the frequency k times 2 pi over n delta t. So those are going to be the points on your frequency axis. Now let's continue here. Same sum still. Still f of Tn. Minus j. And now here's where we're going to use these expressions. So the 2 pi over n comes from the frequency. The k and the small n come from frequency and time respectively, and the delta t's cancel out in the exponent. We're going to change.
There's no way you're multiplying by delta t at the end either?
Good point. And this is exactly the same story as we had with 1 over t naught. But indeed, we did take that out. And we'll, again, take it back in when we go back to the time domain.
I'm not sure I quite understand why it works to take it out. And
How is
that?
So it's not like it doesn't do anything. It does change the value of the expression. However, the expression that you're left with is still going to give you how much of a frequency there is in your signal. It is not, so it's not, there's a factor that you're dropping, so it's not entirely equivalent to if you wouldn't have dropped it, right?
Yeah.
But it still has the right properties and the right shape. So, and it still contains all that information. And yeah, I'm not sure how to formulate that. So we're not looking for an exact equivalent of the series, but rather something that contains the same information, and something that you can extract. You also want to be able to go back to the time domain, but that you can do still because you take it back at that point.
Okay.
Does that make sense?
It makes enough sense.
All right. Feel free to ask Wim for more.
Okay.
I'm sure he has a deeper explanation of it. But all right. And at this point, really the only thing we're going to do is a change in notation. And we're going to use capital X of k for the transform. F of Tn becomes x of n. And then in terms of, or instead of the exponential, we're going to use capital W with the capital N on the bottom, and then to the power kn. So the exponential of minus j 2 pi over capital N becomes W, and we keep the exponential kn out. And we want easier notation here because we'll continue working with this variable, and I don't want to write that, a million times over. And this factor, the W, is called the twiddle factor. And that is really all there is to discrete Fourier transform. So I'll go over here and look at the inverse transform again. Calling that small f a of discrete time, Tn. So going from the expression on the bottom here for the continuous transform, inverse transform. 1 over 2 pi times the sum so here we're going back, so we're using the transform. Sorry. So Fa of j omega k and the exponential j omega k Tn with the delta W, so the steps in W. As we continue here, we're going to change the summation range. And we're going to start at 0 because these frequencies are equivalent. So you can shift your range of summation. We'll have still the same Fa. And here, we'll do really the same thing as we did over there. So 2 pi over capital N. And then the delta omega is, so these are the different omegas, right, with index k. So delta omega is the difference between omega k and omega k plus 1. So if you fill in 1 for k here, you get 2 pi over n delta t. All right. Now, again, similar to here, we're going to change the notation to the x's. So small x of n. And these 2 pi's cancel out. So denominator here, numerator there. And we're going to take that 1 over n, put it in front. And here again, that same twiddle factor, except with a negative exponent. And you can see that indeed the exponentials they're coming from are the same except for a negative sign in the exponent. So these do look very, very similar. There's that negative in the exponent, and there's the factor before the summation. But this means that when you have a function in the time domain and you're transforming it to the frequency domain, it's a very similar thing to what you do actually in the reverse direction. All right. Any questions at this point? Now, next up is an algorithm for, yeah.
Sorry, I missed something. Where did X and K come from?
This one?
Yeah.
So x of k is alternative notation for capital FA
Oh, okay.
of j omega k.
Okay.
Now the thing with these discrete transforms is that these are used a lot. It's basically the first thing you do a lot of the time when you're analyzing anything. But whenever you want the power spectrum or you want to look at the frequency content of any signal, this is what you do. So it's everywhere. It's used a lot, and oftentimes it's used for very large data sets. And we'll do a little example here with a data set of length 4. But you can imagine that if you're using a very large data set and you have to do this every time, you want something that does it as fast as possible. And if you look at this, these are the points in your frequency domain. And for each one of those, you're taking a summation over all the points in your time domain and performing a multiplication there. So for each point in your time series, say you have n points, or capital N points, you have n squared multiplications to do. And pull this up. Instead of doing that, you can actually split the sums. And that's what I'll be talking about. And it's called, I'll start here. It's called FFT, for fast Fourier transform. And this was devised by Cooley and Tukey. In 65, sorry. So let's take a 4-point example. So we have our time series, x1 to x3, or sorry, x0 to x3, so 4 points. And we want to find our discrete Fourier transform, so capital X, 0 to capital X3. And if we take that formula quite directly, we get a sum over 4 elements. Capital N is 4, so we're going to use that for the twiddle factor. And then k times small n. So the first thing in this algorithm is that you split this sum into 2 parts. So you're going to say that this is equivalent to taking the odd and the even elements separately. First part is a new variable r from 0 to 1. So these are going to be your even parts to the sum. And then the twiddle factor at 2rk. Now for the odd elements, the same sum over r. But now odd indexes to x, so 2r plus 1. And also an exponent here. And this twiddle factor to this power, you can split into the 2r plus 1 and k. All right. Now let's look at how this starts to look and how many multiplications we'll have to do. Starting at x0. So I'm just writing out those sums here. W4 to the power 0, which will end up being 1. Then x2, because we're looking at the even elements first. Now for the odd ones. Should have given myself more space, but let's see. I'm sorry, which split? These W's? Yeah. You're taking so because it's an exponential, you can, so if you're taking something to a power, say a plus b, then right. Yes, that's right. Yeah, sorry about that. Yeah. Yeah. Thank you. All right, continuing the last element here. So the last odd x. I'll continue to write these out. For the odd ones, 2. Just one more. I don't want to write these out because they're going to be equivalent to some MATLAB code I'll show you in just a minute. All right. Now, a really important thing to this algorithm is that these twiddle factors are periodic. So they're exponentials, complex exponentials. And what they do is they really go around the complex plane. And what happens is that you have your omega, or your twiddle factor at 0. Now anything to the power 0 is 1. So this is the real number 1. And then in this case, because we have a length of 4, it's going to be periodic with a period of 4. So we're going to have the twiddle factor at 1 on top. Sorry, 1 here. And then we come around. And we have the 5th one back here. And similarly, sorry, 3. I'm sorry. So 3rd one on the bottom. 4th one is round. And then the other one we need is number 6. So 4, 5. 6 is also going to be here again. So that means some of these twiddle factors are going to be equivalent to one another. I'll start this up. All right. This will take a little bit to load up. So here's a program that really does exactly this calculation. The increments in the indices are because MATLAB likes to start at 1 instead of 0, and I use 0 here. It defines the time series up top, the twiddle factors below that, and then those longer lines are what I did here. And you see that it uses the equivalence, or rather the periodicity of the twiddle factor. So instead of going to 4 and 6, for example, in these places, it uses 0 and 2. And that's where you get your reduction in the number of multiplications you're doing. So here, for example, if you remember, you do 16 if you just do it straightforward, right? We had that sum where you have 4 multiplications for each element. Here that's being reduced. And for example, these last two are equivalent to the former two, so you just use the calculation you already made. And similarly on the left side there. And what this program actually shows you when you run it, this is program 7.1, by the way. Is that, so in blue it is the hand-programmed FFT, and it overlaps exactly with the values that you get from the MATLAB routine FFT. So you certainly don't have to program this yourself in general, but we want you to see it in this course so that you know how it works. All right. Yeah.
So what is this graph showing?
Oh, I'm sorry.
So program 6.1.
Yeah.
Program 6.1, yeah. So the axes here are the complex plane.
Okay.
So each of the points you see here are the capital axes. So x0, x1, x2, x3.
Okay.
And they're on a plane because they're complex numbers.
I see.
Does lead very nicely into the next part I wanted to talk about, because yes, what you end up with here is indeed a row of complex numbers, and typically, when you want to look at frequency information, you want to look at the power at different frequencies. So just in a simple real number, how much of a certain frequency is there? And really what you do is you take the magnitude of your complex numbers at any point. So you have your xk, capital Xk, and you have a complex number. So it's your real part, AK, and your imaginary part, BK. Now, taking the magnitude here, you multiply x of k by its conjugate. So you have this expression, ak plus j bk, times ak minus j bk. Conjugates were discussed earlier in the course, right? And what we end up here is ak squared plus bk squared. So the cross terms here cancel, and the quadratic term in BK, you have one minus sign, but then you have j times j, and j squared by definition is minus 1.
So a squared and b squared.
Sorry?
Is a also squared? And b also squared?
Yeah, ak squared and bk squared.
Oh, okay.
And the power spectrum is really exactly that. But normalized by the number of points in your time series, or your transform, because it's the same number. And the normalization is done because it leaves you with the same amount of energy, so the same sum of squares in either domain. Another thing that is sometimes used, not as much as the power spectrum, is the amplitude spectrum. And it's really just the square root of this expression. With another normalization 2 over n. And this means that if you have a sinusoidal signal before you take the transform, then you end up with the same amplitude here as you had in your sinusoid. The last thing here is the phase spectrum. The arctangent of the imaginary part of your capital axis. The imaginary part of your of your transform over the real part. So it's the phase in the imaginary or in the complex plane, and also the phase of the sinusoid in your original signal. All right. Now I should talk a little bit about units in all of this. And so we already found that you have the same number of points in your time domain signal and in your frequency domain. But what about things like resolution in ether and range? So let's say we have our time axis, and we've done a recording for 10 seconds. Evenly sampled data. And our sampling rate was 1 millisecond. And we've done our transform to the frequency domain. We already know we have the same amount of samples. But what about the range here? And this resolution. Now for the range, so we're going to start at a frequency 0, meaning the DC component. But how high can we go with the frequency? And this really goes back to what was talked about earlier in the course, where you can sample up to specifically half the frequency of your sampling frequency, the Nyquist frequency. But it really comes down, first of all, to the inverse of your of the time between samples, in other words, the sampling rate. So for now, let's take that direct inverse. 1,000 hertz, so 1 millisecond is 1,000th of a second inverted. And why with the Nyquist frequency you can only use half of that goes back to what was discussed earlier. I'll let that go for right now. Now the resolution similarly relates to how long your recording was. So this goes back, this gives you the smallest frequency you can measure. And signals of a very small frequency have a long period. So the longer of a period you take, the smaller the frequencies. The smaller the difference between frequencies you can distinguish. So likewise, this is also again an inverse of the range there. So you can have 1/10 of a hertz. Does this make sense? Any questions? All right. Now let's have a look at a program that actually takes a Fourier transform and then displays it also using this information. All right, so we have a sampling rate of 1,000. The number of points we're taking for the FFT. So in FFT, you'll generally want to take a power of 2 as your number of points, because it does build your answer as this sort of tree where you get twice as many points in every step. You can take an FFT of a different amount of points in MATLAB, and it'll just pad it with zeros. But in principle, you should use the power of 2. So we're going to have 512 points. The range for the spectral plot, and this is where Nyquist comes in again. So instead of taking that full range, we're only going to take half of it. And really, if you would see the whole spectral plot, you would see two equal halves. So there's really no extra information contained in that other half. Now the time axis, so it's 1 over the sampling rate. The frequency axis, so this goes up to the range. So this is this value, or the Nyquist frequency rather. And then it defines the function, adds some noise, and then here in line 21 is where it actually takes the FFT. So in this case, it just uses the MATLAB routine. PYY is where it takes the power spectrum. So y is multiplied by its own conjugate, normalized, and then plotted. And I'll run it to show you. So on the left here is our signal. And it is good to realize that it's pretty hard to tell anything from looking at it directly, right? You can't tell that it's composed of 2 sines and some noise. So it is really quite a helpful tool to turn it into what's on the right here, the power spectrum. You see big peaks for each frequency, and then some noise around it. Similarly to where we had noise in the time series. I believe that is all I wanted to discuss today. So I'll ask once again, are there any questions? No? All right, in that case, I'll give you the homework for next week.